here to present our project, which is called Estimator. Let me move back here. So each transaction on the blockchain network, Ethereum network, is associated with some cost. We estimate that cost based on individual opcodes as defined in Ethereum yellow papers. Now, our question was how accurate this cost, nominal cost defined in yellow paper are in, compared to real execution cost. And this question is not just to satisfy our curiosity. We want to know it because it does support the variety of clients found on the Ethereum network, but also inadequate, inaccurate cost can open the network to some possible security issues or vector of attacks. If a specific cost favor some setup software or infrastructure, it might lead to some less decentralized network, or even the code quality. So we know some cases when cheaper opcodes are abused in order to achieve the same effect, but it works, but it leads to some worse code quality. So what we wanted to do in our project is to come up with some standardized methodology to calculate what's the real cost of executing opcodes in the reality, maybe pack it in some automated tooling that can be reproduced everywhere. We chose our reference machine. We are quite aware that one size doesn't fit all, but we had to reference to something. And then we thought, okay, so what we want to measure? The first answer was what we don't want to measure. So there's a lot of unfavorable factors that shouldn't be measured, or in our opinion shouldn't be measured, which comes from cache, warm-up, and so on. It doesn't mean that those factors don't matter. They do matter. It's just that taking them into account would lead to some inconsistent, unfair, sometimes biased results. So we want to remove all of them from our final results. What we want to measure then is we look at the top 7 EVM implementations. We took the EVM interpreter, EVM engine out of it, wrap it in some host, minimal host to satisfy its needs, and then we feed it with bytecode to execute, lots of bytecodes. And we measured it using some most standard tools for every language framework that exists though. After much discussion, we prepared a series of bytecodes which look like that. So we take one bytecode under test, wrap it in some other bytecodes, and then we gradually increase the number of bytecodes and measure the time it takes to execute it, which produce a result like this. So we can, at the bottom line, we have an increasing count of opcodes. We can see how the time measured to execute our full package increases as well. We see that there's a base as well, because all our timing starts in this case from 2600 more or less. The base is to satisfy all the other wrapping bytecodes. On top of it, we said there are some opcodes which depends on the size or the value of the arguments. We have to measure that as well. So for all 120 or so opcodes, we said we wanted to see how the arguments actually affect the time to execute. So here's a sample result. We can see that while we increase the size of second argument, argument 1 in this case, the time to execute exp opcode increases as well. Okay, so now we have the method to measure it. We know what to measure it, and after running a lot of measurements, we have results expressed in time, in nanoseconds. What we can do with these results? Now, the long way would be to compare the nanoseconds directly, because it's comparing apples to oranges really. So all of those EVMs come in different format. We measure them with different tools. So what we did instead, we scale them to the common denominator first, and then create the alternative gas cost schedule, which we can compare to the current gas schedule. Now, the keywords here are the scaling and creating, because behind those words is the whole apparatus that we employed in order to provide some fair and unbiased comparison. More details on it, it's all in our report. I show you later the link, but just to point out that it wasn't an easy step. It was a lot of discussion, and some decisions had to be made how to scale it and compare. So this few graphs show some simple results. We can already observe some interesting behavior. So if we take the top left, that's the typical one. We increase the number of opcodes, the time to execute increases. If we look on the two on the right, it follows mostly the same pattern, but we can observe that the first few opcodes behave in different characteristics. I'm pointing it out because later it plays important role how do we want to incorporate those different behavior into final result or not, or how do we estimate it? The other interesting one is on the bottom left, which is a Java implementation. We can see a nice solid base, and most of the results come on this, but then some of the measurements take much longer time, probably due to some of Java internals, garbage collection, and so on. We can only guess. Now, so this was just measuring the time of single opcodes. This one here measures the arguments. So a bottom graph displays a familiar fashion. We increase the size of argument, and the time to execute that opcode increases as well. The bottom graph is quite different, so some of them follow the same pattern, but other, meaning that this client, Besu in this case, has some kind of smart optimization, and some of the values are executed in constant time, right? And the question arises, how do we incorporate all of this information in the final estimation of the gas cost? Okay, having all the results, we for each client EVM implementation, we prepared this kind of a summary. So even client development teams find it interesting that they can actually see how the engine behaves and what might cause some inconsistencies. So in this case, the top one is Erigon. Interesting thing here is the push 1 to push 32 actually causes more time, while we know that all pushes really push 32 bytes. So that's interesting. On the other side, we have some quite a long, big spread on, I think there were things like a self-balance and return data copy, which behave quite differently, and client implementation team can look into why it behaves that way. Okay, so when we have results for all the clients, we scale them and we can put them on one single graph. On the left, the first one from the left opcode is the add opcode. We can see that most of the clients behave in a similar fashion, so those dots each indicating a client are quite close together. Some of the opcodes have more spread. So everywhere when we have a spread, that causes a trouble for us because we don't know how to really estimate this specific opcode. Now, when we have these opcodes, we can do the scaling, the scaling is done. Do they create a new gas cost schedule or alternative schedule and compare them to the existing one. So the gray dots here is the existing one. The blue dots is the new alternative schedule. We can obviously see that the pushes are here, are affected by what we saw earlier, that two of the implementations have pushes inconsistent. But apart from that, it looks very similar. So add is where it should be. Dupe and swap opcodes are more or less where it should be. So, and we like similar because we defined a good alternative schedule as the one which is similar to the existing one as possible, because we don't want to create completely new world. We want only to adjust those opcodes which are clearly inconsistent and might be a good candidate to change the gas cost. So if we look at the table from the beginning, here are some results. So the first opcode, which is add, the nominal current gas cost is 3. We can see that all the implementations consistently executed at 2. The last column is standard deviation from the results, which takes into account all the clients. So the client variability here is at 10%, which is quite low. So it means that most of the clients really execute add at 2. If we take the last example, push, which is similar. So nominal gas is 3, clients executed at 2. But the client variability is here at 34%, which means that some clients executed better than 2, some other clients executed worse than 2. So it might be not a good candidate to say, oh, we want to update that opcode gas cost to 2. Another interesting example that we can show is the M-store. So it still has some reasonably large client variability, here 28%. Nominal gas cost is 3, but we can see that most of the clients, all of the clients really executed in much worse fashion, so at least 7 gas units to execute it. So even for this large client variability, it might be a good candidate to actually say, hey, it costs node operators really more to execute this specific opcode. Maybe we should update the gas cost. Now, the project is not complete. We've already have completed 3 stages, produced 3 reports, but it's not a job done yet. We still want to work more on automating our tooling definitely including other people to run our tools in an environment that we couldn't envision, couldn't figure out what are the specifics, and then we can compare the results. One omission from our reports are the storage opcodes, which is the S-load, S-store, because they proved to be very difficult to calculate properly. But it's still work in progress. All the raw data, our methodology, decisions that we make, some interesting alternative decisions to calculate gas costs or produce a different gas schedule. It's all included in our report, which I definitely recommend having at least a look or definitely having the proper read and analyze it. And if anyone wants to execute the measurement, feel free to do it. It takes about a few weeks to execute a full package, but definitely shorter execution paths that you can take and do it yourself. So thanks for your time, and that's what's our project.